Okay, welcome back everyone. We are continuing to talk about DC circuits, and in this video we're going to be talking about Kirchhoff's loop rules, and we'll also look at compound circuits. So last time we had looked at rules for series and parallel circuits, and the rule for voltages in series circuits actually leads to Kirchhoff's voltage law, which says that the sum of the potential changes or drops or gains around any closed loop is zero. So imagine that we take this circuit shown here and we cut it so that this is point A. And then we sort of lay it out in a straight line like this. And we mark that as our x-axis, the position within the circuit. Okay? So this voltage that we get from the battery, V0, is going to be a voltage gain. So you can see the voltage going up, because that's what batteries do. They use a chemical reaction to physically separate charge, which creates a potential difference. And in this case, it is a positive potential difference. The chemical energy is doing the work to do this. But as we've talked about previously, then when we go through a resistor, such as R1, we have a voltage drop. So at any point, as you move away from the positive end, the potential is decreasing. So you get a voltage drop as you go through resistor R1, and that's equal to IR1. That's Ohm's law. Then, as we go through resistor R2, we get a second voltage drop equal to IR2. And notice that we model this, that going through a wire, you don't have any voltage drop. And that's pretty close to accurate. We try to get wires with very, very low resistances, so we don't really lose any energy. But then by the time that we've arrived back at point A, we should have zero potential once again. So we start at zero and end at zero. And so a formal way to write the loop law for voltage is that the sum of the individual voltage drops is zero. Okay, so that's kind of the blue statement in math terms. Now, how does this look in a series circuit? Well, so here's our circuit, and we know that the total sum of voltages comes out to zero. So V total, which is from the battery, plus negative IR1, that's our first drop through the first resistor, minus IR2 equals zero. So V total is equal to IR1 plus IR2, and it's also equal to IR total. So what we're doing here is we're sort of re-deriving our equation for the resistance in a series circuit. That is just the sum of the individual resistances. And notice that that I cancels out. Okay? So this is the effective or equivalent or total resistance. It all means the same thing. Okay, now Kirchhoff's second law is the current law. Okay, and this is sometimes known as the junction rule. And the junction rule says that the sum of the currents flowing into a junction is equal to the sum of the currents flowing out. So if you look at point X right here, I going into X is equal to I coming out of X. That is the junction rule. We talked briefly about that in the previous portion of this lecture. And so at point X, what's going into it? Well, it looks like I is the only current going in. And what's coming out? I1 and I2. And we can translate that up to here. And because I is equal to V over R, this is another way of proving our concept that 1 over R in parallel is the sum of 1 over R individual. So that's an example of what the junction rule is. Okay, so how do we use it? So here's a circuit that is a compound circuit. It's got two resistors that are in parallel, the 6 and the 2, that are then in series with a 4 ohm resistor. Additionally, we have more than one voltage source. And in real life, you're going to have multiple voltage sources for an electronics component. So what I've done here is I've drawn two loops, a red loop and a blue loop. And we can write a couple of equations here to describe what's going on. And I should also point out that there is a third loop, which would be obtained by going around the entire circuit, sort of on the perimeter, not going through the middle. Okay? And one very important thing to point out is that when we go through a resistor, if we go in the direction that current is flowing, then we have a negative voltage drop. But if we happen to go opposite our predicted current direction, then we would have a positive current drop. And we'll see how this works out in a moment. So we want to find these three currents, I1, I2, and I3. We want to first guess which way we think the current is traveling around the loop, and it's okay to be wrong because the math is self-correcting. And notice that what we've chosen is basically to try to go the positive direction through both of the batteries. So we're going to use the voltage law and the current law, otherwise known as the loop rule and the junction rule. And in the red loop, we have V minus I3 times 6 ohms minus I1 times 4 ohms equals 0. And that's actually 24 volts. Okay? Now, why is it I3? Because as we go through this resistor, that is what we have called I3 right here. And it's actually on both sides of the loop. It's just I3. So the red loop has an I3 and the blue loop has an I3. And that means that 24, starting here, minus 6I3 minus 4I3 equals 0, or 24 equals 6I3 plus 4I1. Sorry, I misspoke. That's I1. Then in the blue loop, we do pretty much the same thing. Okay, so we go through the voltage, and then we go through the 2 ohm, which is I2. So minus 2I2. And then again, we have minus 6I3 is equal to 0. So we get 12 is equal to 2I2 plus 6I3. Now the problem is that we have three unknowns, I1, I2, and I3, and that's why we need the junction rule, which states that at this point right here, I1 going in plus I2 going in is equal to I3. Okay, so now at this point, we can go ahead and solve. So let's go ahead and solve that. Here's our diagram again, and our three base equations are 24 equals 6I3 plus 4I1. We also have 12 is equal to 2I2 plus 6I3. And then what I'm going to do is substitute for the fact that I3 is equal to I1 plus I2. Now go ahead and pause if you have to kind of figure this out, but that's going to turn into the system 24 is equal to 10 I1 plus 6 I2, and 12 is equal to 6 I1 plus 8 I2. And then I'll multiply this by -4 and plus 3 to eliminate I2. And I'm going to get -60 is equal to -22 I1, which means that I1 is going to be 60 over 20, or 2.73 amps. Now, the first thing that we note is because I1 is positive, that means that we've done this correctly. Okay? We can take that I1 and plug it into either of our equations, and I'll just do the let's see, I can do 12 is equal to 2I2 minus 6 times I1, And what I'm going to get when I solve this is a little bit troubling. I'm going to get that I2 is equal to negative 2.19 amps. You might get slightly different depending on rounding. But what this says is that I2 is actually opposite from what I have drawn. Okay, and that's all right. That just means that I2 is going this way, and this way, and this way. Okay, so really what I should have said is that I1 is equal to I2 plus I3. But that's the thing. You don't know when you set these up. You just have to solve it out and guess. So I2 is actually equal to 2.19. Okay, and then we can solve this for I3. And we have to use our corrected version of this. So that means that we get I3 is equal to just about 0.545 amps. Okay, so the next slide kind of goes through this a little bit faster, and you can take a look as you have time that I3 is 2.18, a little bit of rounding, I1 is 2.73, and so it should have been I1 is I2 plus I3. Okay. And basically what we just did was a compound or a complex circuit, which means that you have some sort of combination of series and parallel. And the strategy is the same. You take the circuit and you solve it from the inside out. So what does that mean? First of all, it means find the total resistance of the circuit. So this is just V. So the first thing is that the 100 and the 50 are in parallel. We use the rule for parallel, and we can draw a new diagram where the 100 and the 50 have been replaced by a single resistor of 33.3. Then that's in series with the 80 ohm, so we have a total resistance of 113. Now, let's say that we had the same circuit, but we had 120 volts. We've already found that the equivalent resistance of the circuit is 113.3 ohms, so now we can calculate the total current. Remember that what we're doing is we're starting with an imaginary reduced circuit that just has one resistor, which is the total or equivalent resistance. Okay, and so that means that 120 over 113.3 is 1.06 amps. Okay, so now what we do is we expand this out, and the voltage would be 120 for this, and because we expand it out one step, then we could have let's see, I have some text here that I'll draw around. So let's say we want to find the voltage drop across the 80 ohm resistor. Okay, so now I'm going to expand back just this far to when this was 33.3 and this was 50. So that was our intermediate step. If we remember from the previous slide, the first thing that we did was we took the 100 and the 50 and put them in parallel. Okay. Well, the thing that we can use is that because these are in series, remember CSVP, that means that the current is 1.06 for the 50 ohm, and then this current, we'll call that I23, is also 1.06. So that means that V is IR, and also V is equal to IR. So that means that for the 80, it's 1.06 times, whoops, I wrote that wrong. That's not a 50, that's an 80. My bad. So that means that V across that 80 ohm resistor is 84.8. And likewise, you can calculate 1.06 times 33.3 is going to be, whoops, let's go back a second, sorry. That's going to be roughly about 35.2 volts. And so that tells us that the voltage drop across the 50 ohm resistor, or the 100 ohm resistor for that matter, is going to be 33.3. Whoa, looking at the wrong thing. It's a Monday. 35.2 volts. So to wrap this up, we've already found the total resistance and the total current, and then we found the voltage across this one is 84.8. What's the voltage across the other? Well, it's going to be 120 minus 84.8, which is 35.2, which is also what we said previously. So there it is. Okay, and finally we could ask the question, what is the current across the 150 ohm resistors? And we know that the current going through the 80 ohm resistor is 1.06 amps, but that's going to split up. And if you think about it, the 100 ohm has twice as much resistance as the 50, but they have the same voltage. Since V is equal to IR, that means that basically I2R2 is going to be I3R3. And if you have twice the resistance for one of them, that means you're going to have twice the current for the other. So basically the 50 ohm is going to get 2/3 of the current, and the 100 will get the other third. So it'll look kind of like this. You take the voltage and divide by the resistance, and you get the current. So 0.352 and 0.704. And you add those up, lo and behold, that's equal to 1.06. And that's exactly what I just wrote over. Okay? All right, so this is where we're going to stop for now. Next time, we're going to start talking about what happens when you add capacitors to circuits. So we'll be deriving equations for the RC circuit.